Okay, part two for the lecture for tomorrow, for Friday, October, what is it tomorrow? 9, I think. We have now talked about the sort of macroscopic phenomenological description of binding, including some of the methods for assaying binding, like scattering analysis, but we haven't talked at all so far, really not much, about what on the microscopic scale actually contributes to binding, what binding looks like, especially when two big complicated molecules like two proteins or a protein in a DNA or something like that come together. I've made a list here of a bunch of different contributions that affect the overall free energy of binding, delta G bind. I've listed 5 different contributions that contribute to the delta H. That is, they are basically sticking types of contributions and can be endothermic or exothermic. They lead to formation of bonding kinds of interactions, sticking kinds of interactions, weak bonds usually. When I say bonding, I don't mean chemical bonding, but weak sticking interactions. Another 5 contributions that contribute to delta S of the binding interaction. All of these contributions, we'll talk about each one of these in some detail down below, but all these contributions together can be used to build either sort of very rough ideas about what might be causing binding or what prevents two molecules from binding, for example, and also what makes binding specific, why two proteins bind to each other but not to anything else. There's 1,000 proteins in the cell. These two guys only bind with each other and ignore all the other 998 proteins. How does that happen? What does one pair of molecules specifically stick to another one in what's called molecular recognition and ignore all the others? And later we'll talk about these same kinds of interactions in the context of switching and cooperative behavior. All right. So you can build a model, either a very rough one, just some ideas, or something actually quantitative that makes actual calculable predictions based on these ideas. These are just rough ideas, but that's what models all are to start with. When you build a model for how something works, all you ever have is some rough ideas to start with, and then you start using those rough ideas to put actual terms into equations and numbers into those terms, and pretty soon you've got something that can predict something. And if it can predict something, then you can test it, right? You can actually make measurements or look stuff up and see if your model actually works, if it matches with experiment or not. Very powerful. It's basically the only way you ever really know what your data mean when you're doing some kind of, especially biophysical kinds of research. So I have this chemical reaction, a binding reaction, P plus L goes to PL. We're going to assume that the structures of all these molecules are known. So P and L might both be proteins, for example. We're going to assume that the crystal structures are known. And therefore we can start talking about whether there's hydrogen bonding going on, whether there are electrostatic interactions, desolvation energy, and so on. All these contributions become something you can kind of see or not see in the structure itself. And then we're going to talk about the fact that delta G of binding has 2 contributions, an enthalpic contribution and a delta S contribution. And so I can write this overall delta G as a sum of contributions, each of which comes maybe from one of these terms. And these are not the only possible, this is not the only possible way of describing all these interactions. There are other ways. But it's at least one set of possible ideas, and you can attribute a certain amount of delta H. You can just basically make a guess a lot of times about a certain, because you kind of know how big these terms are from earlier and other research. You can kind of make a guess for how big this term should be, how big that term should be, and so on. And that gives you, when you put all these guys together, that gives you a guess for how big the overall delta H is. And likewise for the delta S, there's hydrophobic interactions, water release, translational and rotational contributions to the delta S, and configurational changes in the delta S, and we'll talk about all those too. And once you have delta G of binding, you can calculate KD values, you can predict fractions bound, you can predict how things will change with temperature, you can make all kinds of predictions to see if your ideas are reasonable or not. Earlier, when we talked about the protein folding model at the end of chapter 10, was it? I think so. We did something very similar to this. It was for a protein folding reaction rather than a binding reaction, but it was the same kind of thing. We had some ideas for what contributions ought to contribute to a protein folding process, used that to make some expressions, some theoretical expressions for delta H and delta S, and use that to make predictions about when things would fold and when they wouldn't. All right, let's now talk about each of these contributions in turn. So I've got 5 delta H-ish contributions here. I'm going to look at each of those in turn. And the first one is hydrogen bonding. Everybody knows what hydrogen bonding is. It's an oxygen, nitrogen, or a fluorine sticking to a loose hydrogen that is also bonded to an oxygen, a nitrogen, or a fluorine. There are acceptors. Those are things like the oxygen, the nitrogen, or the fluorine, and there are donors. Those are the hydrogens attached to the oxygen, nitrogen, or fluorine. And if I have some ligand L here and I put it into a binding pocket on a protein, very often what you'll see is that there's a set of hydrogen bond donors or acceptors on the protein that matches up with corresponding donors and acceptors on the ligand. And you might say to yourself, hydrogen bonds are strong. If I have 4 hydrogen bonds here, that's going to contribute about 80 kilojoules per mole to the binding energy. That's by itself enough to make a really strong binding interaction. And that's true, except that this ligand had to come out of water in order to stick itself into the pocket. And that means you had to break a whole bunch of hydrogen bonds between the same molecule and the water hydrogen bonds too. And so when you're taking this L out and putting it into the pocket, you're not necessarily gaining any hydrogen bonds. In fact, you could easily lose hydrogen bonds. And the hydrogen bonds in the protein aren't necessarily of the same strength as the ones in the water. Usually they're a little stronger, in fact. So you might gain a little bit of binding energy, break the water, the weaker water ones, make stronger new protein ligand ones, but not necessarily. It can easily go the other way. Likewise, when the protein itself doesn't have a ligand bound, then there's water usually filling up the pocket where the ligand would go, and those waters can hydrogen bond also to all of the donors and acceptors in the pocket. So hydrogen bonding can contribute to binding. It can even contribute to repulsion, to the opposite of binding. It can contribute to dissociation, depending on the strength and the number of hydrogen bonds that you gained and lost in the course of binding something. So there's always a trade-off between the hydrogen bonds you lost to the water and the new hydrogen bonds that you gained when the ligand bound. What that means as a practical matter is that though hydrogen bonding can contribute significantly to binding, usually it doesn't. Usually it contributes to specificity. It's the pattern of hydrogen bonds here that allows that ligand to bind to that pocket, but not some other ligand to bind to the same pocket. So the hydrogen bonding oftentimes helps control, it makes a lock and key arrangement that helps it control the specificity of binding, but not necessarily the strength of binding. Here's an example of that. There is a step in the pathway to produce cholesterol that it's carried out by an enzyme called HMG-CoA reductase. And there is a drug, a competitive inhibitor for HMG-CoA reductase, basically this drug, atorvastatin or Lipitor, binds in place of this molecule, HMG-CoA, which is the natural substrate of HMG-CoA reductase. And so it's the binding of this drug that's important, and the people who developed this drug used the ideas that we're going to be talking about and that we talked about above already to some extent in order to design an inhibitor that would bind in place of the natural substrate. The inhibitor has to bind more strongly, right, than the natural substrate itself because it's got to displace the natural substrate. You want to saturate out all those binding sites on the protein with inhibitors instead of the natural substrate. All right, so let's see how that works. Here's the natural substrate over here, and then 3 different inhibitor molecules that were all designed and all work to some extent or another, binding in the same pocket that the natural inhibitor does. Let's look at that pocket. We can't really see too much. I mean, this is a surface picture of the binding pocket for our enzyme, HMG-CoA reductase. And what you see, or what you learn by looking at the crystal structure in this case, is that this part of the molecule down here on the natural substrate has a whole bunch of donor and acceptor, hydrogen bond donor and acceptor groups. But it also has up here further a hydrophobic region, a relatively hydrophobic region. It's not real hydrophobic. I've kind of outlined in gray here where the hydrophobic regions are, but it's not real hydrophobic. So there are corresponding features on the protein. Here is the place where there are hydrophobic residues on the protein that match up. Greasy residues on the protein that match up with the relatively greasy area for the true substrate, the HMG-CoA. And then down here in this purple region, there's a bunch of hydrogen bond donors and acceptors that are spaced out in space, located in space, in a way that would allow nice hydrogen bonds to form to this part of the molecule. This is really sort of the fingerprinting or hydrogen bonding pattern part of the molecule. So the guys who were designing these drugs said, okay, this is how the natural substrate binds. Let's see if we can mimic that first of all and make it even stronger. And they mimicked it by giving it a region that has the same hydrogen bond pattern, or a similar hydrogen bond pattern, so that it will bind in this hydrogen bonding region. But they gave it an even bigger and more hydrophobic region, so it'll bind stronger. It's the hydrophobic effect that mainly results in the strong binding, and the hydrogen bonding effect that gives it some specificities, because you don't want your drugs to bind everywhere, right? The drugs are already bad enough to put in your body. You don't want them binding. You want them binding just to the one target, not to everything on Earth. So you want some specificity. That's what this guy does for you. But you also want strong binding. That's what the hydrophobic does for you. And all these drugs are the same way. So this one is atorvastatin. That's the one we talked about up above. There's another one, mevestatin here, and another one, fluvastatin. And they all have very similar design, right? They've got a hydrogen bonding region, and they've got a hydrophobic region. And so they all bind basically by the same principles, and were designed, I believe anyway, by the same principles. So here's the basic idea. You've got some hydrogen bonding pattern, and the hydrogen bonding pattern gives rise to specificity in general, but not so much to binding strength, because water molecules replace your molecule when you take the molecule out, and likewise water molecules surround your molecules when you take the molecule out. And the hydrophobic region is then the thing that's responsible for the binding strength. We'll see that again later on when we look down at the hydrophobic effect. The hydrophobic effect is an entropic effect. So, and I have things organized by delta H first and then delta S, so we won't get to hydrophobic effect till we get down a bit, but we will look at that also later. All right, so that's one contribution, the hydrogen bonding, a nice and important contribution for specificity, not so much for binding strength. Another contribution is electrostatics. So that's these two terms, both of these terms, among our list of 5 contributions to the delta H. There are electrostatic interactions, but then there's also a contribution to the electrostatic interaction that we'll call desolvation. I'll explain what that is now. So the electrostatic interactions are charges or charged regions, polar regions on a, let's say, a protein surface. So you've got 2 big molecules here coming together, 2 proteins, say, but it doesn't have to be 2 proteins. It can be a protein and a nucleic acid, or protein and a smaller molecule, or 2 small molecules, even for that matter. And on one of the molecules, there's a pattern of plus and minus charges. And plus charges interacting with plus charges are repulsive, right? Minus with minus also repulsive. So if you want the electrostatics to contribute to the binding, or at least not destabilize the binding, then you want a matched pattern, a complementary pattern of plus and minus charges on the 2 surfaces. You want there to be a plus next to a minus next to a plus, and so on at every single spot along the way. And if we look down here, here are some actual calculations of that. We'll come to those, but you can see these red and blue regions. Red is negative, blue is positive, and we'll look at these a little bit harder, but you can see that they are matched up with each other. That's a general feature whenever 2 complex molecules come together. Yeah, so if you have a bad match here, for example, 2 negative charges next to each other, they're actually going to push the molecules apart. They're going to lead to, they're anti-binding, not binding. Okay, so that's all very good. When you bring these 2 molecules together, you get attractive interactions that help stick the molecules to each other. But just like with the hydrogen bonding, there's a price to pay for that. And that price comes from the fact that charged groups like amines, charged amines, or charged glutamic acids, negative glutamic acids, or something like that, are also very attracted to water, or to counterions like chloride, or magnesium, or sodium. Anything charged in solution, or anything polar in solution like water molecules, are also attracted, very strongly attracted to charges. And if you're going to bring these 2 molecules together, you have to you have to take all those waters away. You have to break all those favorable interactions. And that's the desolvation energy. It's the energy required to get all the solvent away from the charges before you bring in your second molecule. And of course, that's unfavorable generally. And so the question is the overall free energy change from electrostatics, including the desolvation, favorable or unfavorable? Is it less than 0? That's favorable, but it could be easily greater than 0. It could be unfavorable, could cost you more energy to pull all the solvent away than you got back when you bring the nice matched charge patterns together. All right, so just to give a concrete example of that, here's a set of 4 different protein pairs that interact with each other. So here's one up here, here's another one here, here's another one there, here's another one there. And here are their KD values, 10 to the minus 14 for Barnase and bar star, very strong binding. 10 to the minus 8, that's not so strong, but still reasonably strong. 10 to the minus 7, even weaker, and finally 10 to the minus 6, weaker yet. So going from over here to over here, we've gone from very strong binding to weaker and weaker binding. And there's more than one contribution to the binding, of course, but I'm just going to focus and point out the electrostatic contributions here. And let me begin by saying that what these are here are what are called electrostatic potential calculations, and we won't talk about what those are. They're relatively complicated. They use something called the Poisson-Boltzmann equation and so on. But the red areas are negatively charged, the blue areas are positively charged, and so what you want is red-blue pattern matching or pattern complementarity. And you can see, especially on this one here, that this one's all solid blue. This one's pretty much all solid red, especially in the area where they contact each other. So that's negative charges interacting with positive charges. This one's not so obvious, but I think that this blue area right here, for example, matches up with these red areas over here and so on. So, and generally here, yes, generally blue over on this side, generally red over on this side, and so on. Here's the actual numbers. Here are the contributions. So we're just going to look at this one column. There's more stuff here, obviously, and we're going to come back to this table later. But just looking at this one column, it has the electrostatic contributions that were calculated from crystal structures using, Poisson-Boltzmann electrostatics. So these were calculated on a computer. These are not measurements. That means they're not so reliable, but it also means that we can actually get these numbers. How you would get these numbers from measurements, I don't even know. The numbers over here on the left-hand side are the total contributions to the electrostatic energy from all different contributions, from both the pattern matching and the desolvation energy. This first number in each case is the pattern matching energy. That's the desolvation energy in each case. This last number is the pattern matching energy. And the middle number, we haven't really talked about this, but that's the change in the energy caused by the fact that when you bring these two proteins together, the charges shift around and move on the surface, and they tend to do that in somewhat favorable ways, and that gives also a contribution to the overall, a change in the overall electrostatic energy. If you look at these numbers, you can see the desolvation numbers this is kilojoules per mole. These are numbers that are bigger than covalent bond energies. They're very large values. So taking the solvent away from the charges that are already on the protein costs an enormous amount of energy. If we look at the pattern matching favorable interactions due to the interactions between the one protein and the other, those are also large numbers, also as big as a covalent bond, or sometimes even bigger. But you notice on average, not quite as big, right? So these two desolvation energies are almost 800 kilojoules per mole or more. And these are big, but smaller. And likewise, generally speaking, well, not in this case, but in 3 of the 4 cases, you lost more energy desolvating than you gained when the pattern came together. And then these numbers in the middle that are the shift are usually, due to the changes in the arrangement of charges when the molecules come together. These are generally favorable and generally pretty large. Overall, they lead to delta H values this one's basically neutral. It's a little bit unfavorable, but not very much either way. This one's strongly unfavorable. This one's strongly unfavorable, and the only favorable one, and not that favorable, a good favorable contribution, but not huge, is the weakest of the binders. It's this last case. So then the overall binding is the weakest case that actually has the only case that's got favorable electrostatic interactions. Most of the time, for these examples at least, the electrostatic interactions are net unfavorable. And so, like the hydrogen bonding case, electrostatics most often aren't the main contributions to the strength of binding. They're usually contributions that lead to specificity. You've got this pattern or you don't, right? If you got the wrong pattern, then you don't get a strong contribution, you get a negative contribution, you get an unfavorable contribution. And so only molecules that have the right complementary patterns will come together, and that means not binding strength, but specificity. And so just like there's a pattern of hydrogen bonds, there's a pattern of charges, and those patterns lead to specificity, not to binding strength. All right, next to last contribution, this goes by a whole bunch of different names, and sometimes it's not always clear in the literature exactly which interaction or which kind of effect people are talking about, but I'll lump them all together here. So these are all quite non-specific induced dipole, ultimately induced dipole kinds of interactions. So they're called van der Waals, they're called stacking, they're called nonpolar interactions. What that means is I've got some molecule here. It's got polarizable atoms in it, but the solvent also has polarizable atoms. There's an induced dipole interaction between every pair of polarizable atoms, no matter where it comes from, whether it's attached or not. And that represents quite a bit of energy overall, because even though each of these interactions is weak, there's a lot of them altogether. But just like with electrostatics and with the hydrogen bonding, you're competing with water. So if you start with two molecules apart, all these, let's call them nonpolar interactions, van der Waals interactions, induced dipole interactions, are present with the water when you bring the molecules together. Now you've got a new interaction between the two proteins, let's say, but are those new interactions stronger than the ones you lost with the water, or weaker? Well, that just depends on the molecules. Can't tell for sure. And since they're fairly weak interactions and fairly universal actions to begin with, these guys rarely contribute very much to the binding strength or specificity. They're not specific enough. They don't have a specific pattern often enough to contribute to specificity. And they don't change enough when you bind or unbind to cause much change in strength either. There is, however, that's the overall statement, but there is an exception. And that's when you have conjugated molecules, conjugated aromatic pairing kinds of molecules, like the base pair, the bases in DNA, or like aromatic residues like tryptophans in a protein. Those kinds of molecules have especially strong van der Waals induced dipole interactions, and they're therefore likely to stack on each other. So you get a big surface area of interaction between the two, and the loose pi electrons are very polarizable, give rise to a big van der Waals interaction on top of that. And so you do get quite a strong stacking interaction between the bases in DNA, for example. In fact, that stacking interaction is much stronger and much more responsible for holding the DNA together in the double helix than the hydrogen bondings are. Very often, in earlier classes, you may have been told that DNA is held together by hydrogen bonds. It really is not, and for the same reason that we've talked about. When you break the DNA apart, those hydrogen bonds get replaced by hydrogen bonds to water. And it turns out that the hydrogen bonds inside the DNA are a little stronger than the hydrogen bonds that get formed to water if you take the double helix apart, but not that much stronger. Most of the contribution to the formation of the double helix, most of the free energy change that drives the formation of the double helix, is due to stacking interactions, not due to the hydrogen bonding. So that's an exception. That's a place where these nonpolar kinds of interactions, these stacking interactions, actually contribute a great deal to the actual formation of the complex. Same thing happens here in the case of proteins binding a substrate. So this is one of the strongest interactions known in biology. It's the interaction between streptavidin and biotin. Biotin is the ligand that gets bound. Streptavidin is one of these molecules. That biotin is a vitamin K thing that's not easily made by bacteria. There's no metabolic pathway for it. And so the bacteria scavenge the biotin from the surroundings. And because biotin is present only in very low concentrations, they want something that really binds hard. And the main contribution to the binding is stacking between these aromatic tryptophan residues and the hydrophobic parts of the biotin molecule. So this is another case where nonpolar stacking interactions make a big difference, make a big contribution, a big favorable contribution to the strength of the binding. Yeah, the overall KD for biotin streptavidin is about 10 to the minus 15. I've talked a little bit, or I've mentioned this molecule, this interaction before. 10 to the minus 15 means you're in the ballpark of a covalent bond type strength. So yeah, this interaction is extremely strong. Yeah, I could talk a lot more about this because biotin streptavidin interactions are very used widely in a sort of technological way. It's important for biological function for bacteria, but who cares about that, right? It's much more important actually for a whole lot of technological applications in the biological sciences. All right, the last contribution to the delta H's, to the delta H contributions here is strain energy. And that just is what it sounds like. It means you have some molecule, it's got a preferred shape, and you distort that molecule, you torque it. It costs energy to do that. The thing responds like a piece of rubber. It's like bending a piece of rubber. It takes energy to bend that piece of rubber. As long as the bending is not too severe, it's a good approximation to say that that bending is a lot like a spring. It's like bending a leaf spring in an old suspension system from a car, or a cantilever like this. And in fact, if you've got a protein, it turns out that there's various different ways of deforming the protein. You can bend the protein, just grab it here and grab it there and bend it. Or you can grab it here and grab it there and twist it in two different ways. Or you can take these two little tabs and pinch them together. Those are three different ways in which the protein can change shape. And it turns out that those three different ways and things like them act independently. You can do this motion independently of this motion, independently of this motion. You can do all three together. If you do this motion, for example, it doesn't know whether you've already done this motion or not. And so they act independently of each other. They act like three different independent springs. And deformation in any one of these springs costs you a certain amount of energy. Deformation in all of them costs you more energy, and so on. A lot of times when a protein or a DNA especially binds to another molecule, it causes a deformation, and that deformation energy is another contribution to the overall delta H of binding for the interaction. All right. That is all for the delta H contributions. The next thing we're going to talk about are the delta S contributions, but we've gone on long enough for today, so we'll save that for next time.